All right, we are back to finish part 2 of Chemical Kinetics, Chapter 15 for TRO, University of Alaska Anchorage, General Chemistry 2. So let's go ahead and just jump right back into it. So where we left off, we talked a lot about rate. And before we get into here, I just want everyone to be aware up front, I am going to take a couple things off the end of this chapter in terms of lecture. I'm going to remove discussion of mechanism because I think the way that this text introduces mechanisms is overly complex and mechanistic, and I think introducing mechanisms via electron pushing in OChem is a simpler way to get about it, and including rate limiting steps and whatnot. Since we've already discussed rate limiting steps as part of chemistry in first semester. And I'm also going to simplify the discussion around catalysis a little bit and focus on elements of it. So if you notice that I'm excluded a couple concepts that are at the end of this chapter, don't worry. I'm not holding you accountable for those specific things. I want you to focus on the things I'm talking about in this lecture specifically. So with that in mind, moving on to the effect of temperature on rate. Now that everything's had a little bit of soak time, it's time to make it a little bit more complicated, naturally, right? Because we spent all this energy looking at rate law, okay, for any particular reaction in the last lecture. But what we're going to introduce now is the reality that that term K is in fact temperature dependent. The rate law depends on temperature. So when we are spending all that energy looking at reaction rate and the rate law, remember that those scenarios are specific to a given reaction condition, a given temperature. And you can change the rate of the reaction by increasing or decreasing the temperature. And what we're going to get into now are the relationships which allow us to model and predict how K will change as we change temperature. Right out the gate, let's take a look at the Arrhenius equation right here. So K, our rate law, is going to equal the frequency factor, capital A, times the exponential factor raised to this, the E raised to the exponent of the negative activation energy over RT, which is our gas constant for R, and T, our temperature in Kelvin. So we have just a couple terms here, and it looks a little bit daunting at first, but this is actually, we're going to simplify it pretty neatly. So A, capital A, our frequency factor, is the rate the reactant energy approaches the activation energy. So we'll get more into those details, and we'll keep revisiting these terms and making more sense of it. But how quickly does a reactant's energy approach the amount of energy required for it to proceed forward, going from a reactant to a product? The activation energy is the minimum energy needed to start the reaction, that barrier that must be overcome energetically for a reactant to become a product. We know what R is. It's our gas constant, 8.314 joules per mole Kelvin, and T is our temperature. And if we're talking about energy and activation energies, remember that temperature is a measure of thermal energy, which translates to vibrational energy in these molecules. So with all this in mind, let's move along and start fleshing this out a little bit. So we're talking about activation energy. I want to take a moment to talk about this plot because it's so important. Notice on the y-axis we have energy. On the x-axis we have reaction progress. And we're going to model just the reaction of hydrogen gas with oxygen gas to form water in gas phase. So 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to form 2 molecules of gaseous state water. And what's really important to look at is at the beginning, the energy of the reactants, the sum of the energy of the reactants are here. Arbitrarily, we'll just call that our starting point for energy. And when we look at the energy of the products, they're lower. And the tendency for chemistry and so many other physical processes in our universe is to go from states of higher energy to states of lower energy. That's really the impetus which drives chemical reactions, going from higher energy to lower energy, which also can be described as going from less stability, being higher energy, to greater stability, lower energy. So low energy, more stable, high energy, less stable. So that's all part of our discussion here. So we're starting with two things that are of a set energy level, and they can react to form products which have a lower energy level and therefore are more stable, so it becomes a favorable reaction. However, to proceed, we have to break bonds and then form new bonds. And the breaking of the bonds requires that those stable things, these bonds, become disrupted, and that takes energy. That's going to cause an energetic barrier to the reaction. So you can think of this as an investment of energy, where if this was a physical hill and we had a ball and you were pushing the ball up the hill, once you got it to the top of the hill and you rolled it down, it would be happier down here in terms of potential energy than it was here. However, but if you don't have enough energy to push it up over the top of this barrier, you're never going to get it down here, because you have to be able to overcome that energetic barrier. So let me just erase some of these things. There we go. So that said, sometimes we have very large barriers to activation of a reaction. Sometimes we have lower barriers to activation. Just because a reaction is highly favorable, which this one is, because the reactants are higher energy than the products, so the products are more stable than the reactants. Even though this is highly favorable, some reactions that are highly favorable have very high activation energies and therefore proceed very slowly or require a substantial amount of extra energy to proceed. Just because something's favorable doesn't mean it's fast. Just because something's favorable spontaneous doesn't mean it proceeds very quickly. What determines the rate of the reaction is the energy level that's available here and the energy that has to be overcome and the delta between those two things. This is why, fundamentally, if you put more energy into the system, we start to increase the temperature, we start to increase the energy available, we close this gap. And by closing that gap, we make it easier for the reaction to proceed. So I'm going to go and probably say this a couple different ways, a couple different times. So don't fret about it now. But it's something, the dead horse of chemistry. I'm going to keep on beating on it. High energy, less stable. Low energy, more stable. Energy, do you have enough energy available to accomplish the task at hand? Things to keep in mind to make sense of all these equations we're looking at. So, activation energy and the activated complex. Like I said before, there's an activation energetic barrier to almost all reactions. There are a few that aren't, but almost all of them have it because you have to break the bonds so that you can reform new, more stable bonds. And that high energy state is our activated complex. The book likes to call it activated complex. I'm almost always going to call it the transition state because I was trained in an environment where we called it the transition state. So the transition state is just a chemical species with partially broken bonds, partially formed bonds. You can also think of them as very elongated bonds that are very weak, where one bond is forming while one bond is breaking. They don't really follow the rules you would expect of bonding when you're looking at a Lewis dot structure, because they're really high energy. They're not stable, and they want to find a more stable place to be. So once we get into this transition state, you have a system where the bonds are partially broken and partially formed. They don't really have an achieved identity yet. Notice we're dealing with these arrows. One forward arrow, one reverse arrow. This is indicative of an equilibrium system, which we'll be describing in a lot more detail in upcoming chapters. But the reason we have this equilibrium system is because at this point, you can have a fate where it returns to the way it was, or you can have a fate where it forms something new. And the ratio of those things is going to depend on the relative energy level of where they started and where they finish, and how much energy is required in transition. So this is, like I said, the shade of gray that I really love in 106. It's not about yes or no, does it precipitate or not precipitate, does it react or not react. It's how much, how fast, in what ratios. So let's take a look at the isomerization of methyl isonitrile. So methyl isonitrile has a methyl group, the CH3 here, attached to the nitrogen side of a nitrogen with a triple bond to a carbon. And the nitrogen to carbon triple bond is very strong. And it's drawn a little bit weird here, because what it looks like in this reaction is that the carbon and nitrogen are like flipping. And I want you to think of this as a ball that's rolling, because this triple bond is not changing. Cyano group is looks like this. It's one of our polyatomic ions, remember? And so cyano groups are very, very strong triple bond carbon to nitrogen, and it's not going anywhere. That triple bond is set here. However, what's changing is which of the what the methyl is bound to. So the methyl in this case, the bond between the methyl group and the nitrogen is going to weaken under high energy conditions, and then it's going to reform to the carbon side of the cyano group. So we have this methyl isonitrile, and when it bonds the methyl group to the carbon, you get the solvent acetonitrile. So this is a really nice little diagram here showing the bond between the methyl group and the nitrogen weakening, and it's starting to roll. And as it starts to roll, the carbon becomes available and a new bond can form. And this is a nice way to look at this rolling process, because if we look at the transition state, you can see that the triple bond is undisturbed between the carbon and the nitrogen. However, we have this kind of broken bond between the methyl and nitrogen, but kind of formed bond between the methyl and the carbon. This is our highest energy point for the reaction, and because of that, it's also our least stable point. So it very much wants to go back to being something stable. And it can either reform the reactant, or it can form the product. And in this particular case, because the product is lower energy, it's going to overwhelmingly favor that. Now you can say, well, what if it goes back down and reforms the reactant? Well, if we have enough energy available to drive the reaction, to overcome the transition state, eventually that is going to run back uphill. It's going to reform your transition state, and probabilistically, eventually, it will find the fate as a product. Now, let me get into the erase again here. Why would, if you can go one way or the other, end up favoring the product? Well, because the difference between the reactant and the transition state is substantially less than the product and the transition state. There is a much larger barrier to activation of the reaction go in the reverse direction than go in the forward direction. So in this particular case, because the product is so much more stable than the reactant, but the threshold for activation is the same, you're going to get a reaction which favors the formation of acetonitrile as the product. I think I just said all these things. Let's see here. Yep, the activation energy is the difference. I guess that's an important point. The delta, so it doesn't matter where we start. What matters for activation energy is the difference between where we start for our reactant and our highest point of energy in our transition state. And the frequency that we were looking at in the Arrhenius equation is the number of molecules that begin to form the activated complex in a given period of time. So it's an expression of how fast are we reaching this point. So frequency factor. Frequency factor is a representation of the number of approaches to the activation energy barrier per unit time. So I keep talking about approaches, getting up here so it can determine its fate, either going back reversibly towards the product or forward towards, back towards our reactant or forward towards our product. And in this case, the book refers to as a WAG, that bond between the methyl group and the nitrogen stretching and bending a little bit. And the more energy we have available in our environment, the more prone that bond, as it vibrates and moves, is going to stretch a little past the point of stability and start to rock into this less stable position, which allows it to potentially reach this activation barrier, where it's halfway between binding the nitrogen and halfway between binding the carbon. This process is entirely energy dependent, and it has to do with the bond's character. So if a bond is a weak bond, inherently, a not stable bond, a high energy bond, it's going to take less energetic impetus to get it to stretch further out of its semi-stable state to a transition state. Now, you have a really strong bond, a really stable low energy bond. It's going to take a lot more energy to get that bond to stretch, lengthen, and to use the book's term, wag, so that it rotates out of plane. So remember, weaker bonds are more susceptible to this wagging, stretching, vibrational motion, which can move things towards an activation energy barrier. Whereas stronger bonds are going to take a lot more energy. However, with enough energy, we can do all kinds of cool things. So, doubling back a little bit more, fleshing out the concepts surrounding the Arrhenius equation. The exponential factor, we have E raised to this term, negative activation energy over RT. So, this is a term which is between 0 and 1, called the exponential factor. And what it does is it represents the fraction of reactant molecules with sufficient energy that can make it over the energetic barrier. So this term basically says what fraction of our reactants are susceptible to crossing over the energetic barrier, forming our transition state. And that makes sense because it's a term which pulls in to combination our activation energy and our temperature, or thermal energy available to excite our molecules towards the activation energy barrier. So remember, the higher the energetic barrier, or larger the activation energy, the fewer molecules that are going to have sufficient energy to overcome it at any given temperature. But if you increase the temperature, that's going to excite the molecules more, and that's going to increase the ratio or the fraction of molecules which are excited to enough degree to pass over that energetic barrier and make the transition state. So, simple terms, increasing temperature increases reaction rate, because it increases the number of reactant molecules which can overcome the transition state of a reaction. And this is a really nice little diagram which demonstrates that. So in blue, at temperature 1, we have a nice Gaussian distribution, which is centered at my awful little red squiggle there. And you can see here we have our activation energy. Only a small fraction of that distribution is able to overcome the activation energy, form the transition state, and potentially form the product. Whereas, if we excite that population of molecules to temperature 2, and we now have a same population, but it's more excited, and of course it's distributed. They're not all exactly the same energy. It's Gaussian distribution. And here we can see a much larger fraction of these molecules have enough energy to overcome the activation energy barrier, form the transition state, potentially proceed forward to form the product. So to summarize, frequency factor is just the number of times a reactant approaches the activation barrier per unit time. The more this happens, the faster the reaction is going to be. The exponential factor is the fraction of the approaches that are successful in surmounting the activation barrier and forming products. And the exponential factor increases with increasing temperature, but decreases with increasing activation energy. So the higher the energy barrier, exponential factor goes down. Higher the temperature, it goes up. Two competing factors working to kind of intuitively increase the rate of reaction or decrease the rate of reaction. And coming back to Arrhenius plot, here we go. So I'm going to zoom back to the beginning. Here's the Arrhenius plot in its classic form. I'm going to show you some different variations on it. And why? Because we like to be able to model things and do things experimentally. So you can algebraically solve the Arrhenius plot to give you a straight line formula. This is definitely going to be a trend you're going to see throughout the semester, as we like to be able to make nice linear plots that give us the ability to predict things and identify things. So y equals mx plus b, natural log of k, in this case. M is our negative energy of activation over our gas law, gas constant. X, 1 over T in Kelvin. B, natural log of A. So a graph or plot of the natural log of K, which is Y, versus 1 over T should give you a straight line. So over a range of temperatures, you measure K over a range of temperatures, plot the natural log of K versus 1 over T, and that allows you to, through the slope, find M, which is activation energy over the gas constant, which is a constant, so you can solve immediately for your activation energy, or you can solve for A by looking for the intercept at B, and then eliminating the natural log. Pretty straightforward. It looks kind of gnarly, but once you do this a few times, you guys are going to be pros at it. Now, this is if you have a bunch of points. What if you have 2 points? Just 2 points. This is the perfect use of this equation for a 2-point. If you have the 2 points for temperature, 2 points of 2 different values of K for 2 different temperatures, just plug them right into here, and you can solve for your activation energy really easily doing this. So topically moving on a little bit. We've gone from modeling a little bit. We're going to dial it back and try to add some intuition to why temperature affects reaction rate and the other things that may impact reaction rate. So this is called collision theory. And I've kind of referred to it earlier in the lecture, but we're going to get back to it and elaborate a little bit more. So the idea in collision theory is that for a reaction to take place, reacting molecules need to collide with each other, right? And this seems like an odd value. I'm not going to quiz you on the number of collisions per second at any particular given temperature. But once molecules collide, they may react or they may not, depending on a couple different factors. And the two primary factors are whether or not they collide with enough energy to overcome the bonding energy of the existing molecules, and whether or not they collide with the proper orientation for that reaction to happen. Are the atoms within each molecule aligned so that the reacting atoms are making contact versus them being turned around the wrong direction? So it comes to is there enough energy in the collision, and are they aligned? Those are really just the two factors. So a good example of this would be, let's see here, what are we looking at? Here we have energetic collision leading to a product. Okay, so we've got, let's say, water and hydrogen gas. Or no, this is NO2 and H2, I think, based on the book's representation. Regardless, when they're aligned with the blue smacking directly between this bond, you're able to get a reaction. However, if you have them misaligned, you'll have no reaction. When we get in, if you are of the mind and interest to take organic chemistry, which is my favorite academic topic, I'm not going to sugarcoat it, we go into really lovely detail showing how electrons on one atom align with orbitals of another to facilitate the transfer electrons from one bond to another. This is a really reasonable simplification for a 100-level course, but if you take it up to organic chemistry, if your interest lies there, or you're pursuing a medical profession or dental profession, or just interested in chemistry, which is perfectly reasonable too as a justification for taking chemistry classes, you'll learn so much more about this than we go into in this particular class. So, frequency factor as part of the Arrhenius equation. So, the Arrhenius equation, originally we just said this term A is called the frequency factor, but really you can break down the frequency factor into the combination of the orientation factor and collision frequency. So, instead of just A, we can sub in PZ. And P is our orientation factor, and Z is our collision frequency. Orientation factor, what we just talked about, but with a better diagram. So here we have two molecules of NaCl, and when they combine, you get 2 molecules of NO and 1 molecule of chlorine gas. Now, to make this happen, they have to be aligned so that the chlorines are in collision. If you get the chlorine colliding with a nitrogen, it doesn't happen. If you have a nitrogen colliding with a nitrogen, it doesn't happen. But when the chlorine collides with the chlorines form a new bond and kick off the equivalent of NO. And instead of bonding electrons being spent between the chlorines and the oxygens, those bonding electrons go between the chlorines, and we get from these two reactants 3 products. But if those chlorines aren't aligned as part of the collision, it doesn't matter how hard they smash into each other or how frequently, it's not going to happen. Now you can imagine that the more complex a molecule becomes, the more specific the orientation has to be for the collision to be effective. So typically, the larger and more complex a molecule is, or a series of reactant molecules are, the lower the fraction of collisions are effective collisions because of having correct orientation. So that said, if you have a more frequent set of collisions, that's going to help too, because just by rolling the dice over and over, more and more and more, you're going to get higher likelihood of effective collision. Sorry, I just skipped forward twice. So effective collision happen more frequently when they molecules are excited or when you have a higher concentration, and that increases the reactant rate. The more collisions per second, the more likely you're going to get 2 reactants which effectively collide with the proper energy and proper orientation to lead to product formation. And this is just a restatement, honestly, orientation factor of P of what we've discussed. Most reactions, P is going to be less than 1, meaning most collisions aren't going to result in a alignment of electron orbitals which facilitate the transfer of electrons to form new bonds and break old bonds. Exceptions being lone atoms, because the orbitals of lone atoms are spherical and all approaches are equal. But whenever you have 2 atoms bound together forming a molecule, P is going to be less than 1. Generally, because for the reasons we discussed just a second ago, more complex reactant molecules are going to have smaller values of P, because the incident of having the proper perfect orientation with larger, more complex structures is lower. And that's pretty straightforward. And once again, this is a reiteration of the things we've already said. Now, catalysis or catalysts. Catalysts are substances which affect the rate of reaction without being consumed. So there's different mechanisms of catalysis that we're not going to go into. But the important thing is that when you start the reaction, the catalyst interacts with the system, and when the reaction is done, the catalyst is unchanged from the way it started. It can go through some changes in the middle, but at the end of the reaction, it's the same as when it started. That's how we say it's not consumed. Sometimes reactions are partially consumed and then regenerated. I don't want to go into all the details of catalysis here. I want to just kind of go through the big picture. So on a surface perspective, catalysts affect rate of reaction, typically accelerate, without being consumed. And they work by providing an alternative mechanism for the reaction. Let's take a look at that. Classically, let's take a look here. We have ozone plus monoxygen. Here, these are high energy systems. They still have a high transition state. So they're going to proceed to forming 2 units of oxygen gas at a particular rate of reaction, which is dependent on the size of this energetic barrier to the transition state and how much energy is available through heat, right? But if you add a catalyst, what the catalyst does is it provides an alternative reaction mechanism which lowers the energetic barrier to forming the transition state. often through multiple lower energy transitions. And that's what we're seeing here. And let me get a different color. Note that the difference, the delta, between the reactant energy level and the transition state without the catalyst is so much larger than it is with the catalyst, that a much larger population of the reactant molecules are going to overcome the new lowered transition state energy level, which will increase the rate of reaction substantially. What it won't do is change the fraction of molecules that become products, but it'll get them there a heck of a lot faster. There are typically two categories of catalysts. Heterogeneous catalysts are in the same phase as the reactant. They hold one reactant molecule in a proper orientation when the collision takes place, and this sometimes helps to start breaking the bond as well. Homogeneous catalysts are in a different phase than the reactant particles, and they react with one of the reactant molecules to form a more stable activated complex with a lower activation energy. So it's just two different approaches to catalysis, but it doesn't fundamentally change what the catalysts are. And my favorite form of catalysis is through enzymes, biological catalysts. When you guys, if you're pursuing a biology degree or a profession which involves medicine, when we get into Biochem 1, we will spend 3 chapters looking at enzymes and catalysis mechanisms via enzymes. And it's just astonishingly elegant machinery which facilitates the control of all of our biological reactions. It's just astonishingly elegant chemistry. So if you're of the interest of it, I highly encourage you to take Biochem 1 down the road. But first you have to take OChem, it's a prereq. That said, what enzymes are they're protein molecules which catalyze biological reactions. And they work through, this is a gross oversimplification, but it's appropriate for 100 level. They take the substrate into the active site of the protein, and that orients the substrate perfectly for the reaction. Instead of talking about it too much, I'm going to show this picture, because what happens is, let's take a look at this sucrose molecule, which is a unit of glucose and a unit of fructose. And they're bound, let me get this color back, through this bond here that I'm pointing at. And we want to break this bond to form glucose and fructose. Typically, this doesn't happen very fast. And we know this because sucrose is your table sugar and it sits around at room temperature, which isn't that far away from body temperature all day long. It's pretty happy to do that. However, if we put the sucrose in the active site of sucrase enzyme, it'll bind perfectly along the enzyme at the binding pocket. And when it does this, the combination of the sucrose and the enzyme forms a new equilibrium. And the enzyme changes shape. And by changing shape just incrementally, it's going to take this bond and stretch it apart a little bit. So instead of being a hard bond like this, it's going to be more like that. And that longer, weaker bond now has a much lower barrier, energetic barrier, for forming the transition state between the glucose and the fructose separating. And now that it's stretched out and broken, it's very easy for one electron to move to one and one electron to move to the other. And you can easily break that bond without heating it up. And this is how biological enzymes, in a very simple vision, function to physically manipulate the structure and orientation of bonds and molecules to facilitate lowering the energy of activation for reaction. It's just really, really fantastic how our biological systems execute chemical reactions. So this is the last slide for chapter 15. I'm going to leave it on a high note. I'm going to make a couple videos specific to problem solving, which we'll be following in the next couple days. And I encourage you to use those to help facilitate problem solving as part of your homework and studying. So that's it for now, and we'll be back with Chapter 16 down the road in a couple of weeks.